Hello, my name is Ali Mahmetov, CST 2409079. Today, me and my friend will be explaining how linear systems can be applied in science and engineering. Linear systems can play a fundamental role in aerospace engineering because they allow the modeling, analysis, and control of complex dynamics processes associated with aircraft, satellites, and space systems. So below are the main aspects of their application. The first one is flight dynamics, linearization of motion equation. Uh, the equation governing the motion of aircrafts, for example, planes, rockets, satellites, and so on. They are represented as a nonlinear differential equations. To analyze system behavior near the specific point, for example, cruise flight, these equations are linearized. Linearization simplifies the analysis of stability and dynamics. Next one is flight stability. Linear systems are used to assess the stability of aircraft. For example, by calculating the eigenvalues of state space matrices, uh, engineers determine whether the system is stable or unstable. So, for example, model of aircraft motion is a longitudinal plane. The equation of motion can be written in linear form, as you can see in the slide, where u, v, q, and theta are the longitudinal velocity, vertical velocity, pitch rate, and pitch angle. Yeah, and delta E is the elevator deflection. Analyzing the matrix A, we can assess the aircraft's stability. Next slide is a flight control. For example, modern autopilot system manages the position, heading, and altitude of an aircraft using linear models such as a transfer function or state space representations. These models enable the design of effective controllers. For example, an autopilot system for maintaining the altitude of an aircraft. You can see the linear model which can use it, where h is the altitude, theta is the pitch angle, and kp and kd are positional and derivative gains. This linear system is used to calculate elevator deflection to minimize altitude error. The next one will be vibration and structural dynamics. Vibrational analysis, for example, linear systems describe vibrations of wings, fuselages, and other structural elements of aircraft. This is especially critical to prevent resonance, which can cause structural failure. Flexible models for flexible structures, for example, large wings or satellite solar panels, linear systems model small oscillations, helping to improve structural and design control. For example, wings vibration analysis. For an aircraft wing, the system of equation can be modeled like shown in the presentation, where M, C, K are the mass, damping, and stiffness matrices, and X is the displacement vector. Solving this linear equation allows engineers to predict the wing's behavior under vibrations. Next one is a satellite attitude and position control. Satellites and spacecraft use reaction wheels, gyroscopes for attitude control. Linear systems describe the rotational dynamics of satellite, aiding in the development of control algorithms, such as orbit calibration and correction. Linear system of equation help calculate maneuvers to maintain a satellite's orbit or correct its position. For example, Euler's equation for satellite rotation in linearized form, where the Wx, Wy, and Wz are the satellite's angular velocity, and U is the control torque. This system enables stabilization of a satellite using reaction wheels. Let's move on to the aerodynamics, the flow linearization. For low speeds or small disturbances, Linear models describe dynamics flow around wings or aircraft bodies. This accelerates computational analysis during design. For example, linearized aerodynamic flow around the airfoil, whereas phi is the velocity potential. Solving this linear system helps to calculate the lift and pressure distribution on the airfoil. Next slide is about the space navigation. It can helps with solving triangular problems. GPS and other navigation systems use linear systems to determine the position and velocity of aircraft in space. This system processes signals from satellites, solving sets of linear equations for the precise calculation. For example, determining the position of a spacecraft using GPS. A linear system of equation where x1, x2, y1, y2, z1, z2, and so on are the satellite coordinates, and d1, d2, d3, and so on are the measured distances solving this system. So we can find the x, y, z, the coordinates of object, and the time of it. So the last one is will be the signal and data processing, especially for the radar and telemetry. Linear systems are used to process radar signals, tracking flight trajectories, and communication systems. Linear methods are applied in satellite communication for signal encoding, modulation, and demodulation. For example, radar signal processing, the signal can be described by a linear system where A is the radar impulse matrix, X is the target signal, and B is the measured response. Solving this system recovers the target signal. For the conclusion, I would like to say that the linear systems in aerospace engineering are a powerful tool that simplifies complex tasks related to the motion, control, and design of aircraft and space systems. They provide the foundation for reliability, precision, and efficiency in high-tech field.
Hello, my name is Namov Yunus and I'm going to tell about applications of linear systems in chemistry. So, linear systems are widely used in chemistry to help scientists solve various problems and understand complex processes. From balancing equations to studying molecular behavior, these systems provide a practical way to analyze and predict chemical phenomena. This slide shows the most common fields of chemistry in which systems of linear equations can be used. The first field is chemical kinetics. In kinetics reaction, linear systems can model the rates at which reactants are converted into products over time. The rate laws can often be expressed as linear equations under certain conditions, allowing for straightforward analysis and predictions. The second is chemical equilibrium. In chemical reactions, equilibrium occurs when the reactants and products reach a balance. Linear systems help calculate the concentrations of all substances at this balance point using relationships like the equilibrium constant. The third is quantum chemistry. In quantum chemistry, scientists use linear systems to study molecules. For example, in Schrödinger equation helps describe how electrons behave in molecule. Solving these systems, solving this system tells us about molecular bonds, energies, and shapes. And the last one is electrochemistry. Linear systems are widely used in electrochemistry to model, analyze, and solve problems involving chemical reactions, electrical currents, and the transport of charged species. This slide about balancing chemical reactions. So, one of the most fundamental applications of linear system in chemistry is the balancing of chemical equations. Balanced equations ensure that the law of conservation of mass is upheld. meaning that the number of atoms for each element remains constant before and after reaction. There you can see one example of reaction. When propan bonds with oxygen, it produces carbon dioxide and water. But this chemical equation is not balanced because the total numbers of atoms of each type on the left side of the reaction must match the corresponding numbers of atoms on the right side of the reaction, because atoms are neither destroyed nor created in this reaction. We have to balance the chemical equation. For this, we will add unknown coefficients x1, x2, x3, and x4 in front of each components. I have x1 and then I'm gonna make a vector, and I look at the first compound. There I have 3 carbon, so I'm gonna put a 3 in my vector. In this compound I also have 8 hydrogen, so I will put 8 in my vector. There I don't have oxygen, so I put a 0 there. Let's look at the next one. There I have x2, and then I'm gonna make a vector and also look at the second compound. There I have 0 carbon, so I'm gonna put a 0 in my vector. I have also 0 hydrogen, so I will put a 0 in my vector. Also I have 2 oxygen, so I put a 2 there. I'm doing the same thing for the right side of the equation also. First let's convert these vector equations to matrix form, so we get this form. As you can see, there is a 3, 8 and 0 like in this vector, and the other vectors also written in this form. We can represent this system of equation as an augmented matrix. The result you can see on the slide. So let's move on the next slide. To solve this system of linear equations, we need to make a reduced row echelon form. So as you can see, it's a reduced matrix with 3 pivot points there, there, and there. So why we have done it? This will greatly simplify the solution of the equation in the future. We need to remember that in an augmented matrix, each column represents coefficients for a certain variable. So I have my x1 through x4 variables, and so when I translate this matrix back to equations, the top row give me this, the second row give me this, and the third row gives me this. So we have only 3 pivot points. For this, x4 is free variable. So now here's a key idea. When you are balancing chemical equations, since the coefficients in a chemical equation must be a positive whole numbers. In other words, you cannot split atoms, so you cannot have parts of each compound. So you have to have positive whole numbers at the coefficients. So we pick the smallest value for the free variable. The free variable is x4. So if I let x4 equal 4, then x1 and x2, x3 will come out as a whole number coefficients. This way I will get a solution to the system equation. In conclusion, I want to say that the linear systems are essential for many areas of chemistry. They simplify complex problems from balancing equations to understanding molecular interactions. Thanks for your attention.